Hey everyone, it's Lucas Campos, and today we're going to be going over Physics 2211 Lab 1 Constant Velocity. So looking at our agenda for today, I'll start off by introducing the lab and then moving into the fundamental principles used along with the data analysis and then comparing that data and then move into some possible errors and then the discussion questions to end it. All right, introducing this lab. So in this lab, I observed a pickleball that rolled across the floor, and for all purposes of the lab, velocity was is to be remain constant. And then I compared those actual observations to a theoretical model that was built in a program called GlowScript. And my initial conditions was my velocity was 3.05 meters a second in the x direction, and time is just 0 seconds. And the system is going to be the ball, which is the pickleball, and then the hand that pushed it, my hand, and the floor that it rolled on. So next off, we're looking into the fundamental principles used within this lab. And we can see here that the updated velocity formula, we get velocity final is equal to velocity initial plus the net force divided by mass times the change of time. And for all purposes of this lab, net force is zero, meaning that the second half of this first equation is um, not considered. So here we get velocity final is equal to velocity initial. And then here we can also see that mass does not have any change in the results of the lab. Moving into the actual program used to track the ball, it's called Tracker. I imported a video of me pushing the ball across the floor, and in real time, I was able to see the position time graph that was made. You can see that here up in the right corner. And this, yeah, once again, just plotted the position of the ball as it moved through the floor and as time increased. And moving on to a different application called GlowScript, here I built a theoretical model of the experiment, and I changed here the ball position, the initial position. This just it's a little off from the origin. It just matched the tracker. And then for the ball velocity, I got the data from the tracker and I found the average velocity for the remainder of the experiment. And then down here, I changed the net force to equal zero. So that aligns with, again, with the experiment constraints. And with the data from the tracker and the glow scripts, I was able to pull that and then compile into one graph. So we can see here the observed position is the from the tracker program from what actually happened. And then the predicted position, we see here it's constant velocity. This is from the glow script model. So there's no net force, it's constant. And here at the bottom, we can see that the velocity, the position, the velocity slows down a little bit here. And then that's probably due to some outside forces. I mean, there's a couple of them. We'll get into that later, but we can see that overall they're pretty similar, and especially in the beginning when there's not much forces acting on it, and then towards the end we can see it deviates. And now we can look at possible errors. So I kind of just went over this, but for the experiment, a lot of errors could have been the friction on the floor, the tracker program itself could not have measured the ball very accurately. And we have area resistance and then shape of the pickleball, so it has the divots and such. So that can definitely lead to some possible errors. Now, finishing off with the further questions discussed and the slash of discussion questions, I was asked what if the axes were flipped? And basically, all this would do is would turn the slope to negative, and the origin would remain the exact same place. And then the next question is, what does it mean if the net force is zero? And is it possible to say how many forces are acting on the ball to yield a zero net force? And the net force is going to be zero if the opposing forces are equal to the driving force. And it's not really possible to determine how many forces are acting on the ball. But again, we have air resistance, friction, and then, yeah, kind of that stuff. And then it's pretty much always going to be slowing the ball down, and the slight chance, who knows, it could also be pushing it and making it go faster. But in this experiment, it slowed the ball down, and the result, the ball did not go as far.